Good morning. My name is Jose Roberto Bermudez Hernandez. The collaborators of this paper are Francisco Ronay López Estrada, Gildas Besanzón, Guillermo Valencia Paldomo, and Citlali Martinez Garcia. This paper is a collaboration with the University Grenoble Alpes. The title is Optimal Control in a Pipeline Coupled to a Pressure-Reducing Valve for Pressure Management and Leakage Reduction. The content is the introduction, problem statement, model description, the case study, control algorithm design, in this case, linearization of quadrant distribution system, prediction equations, constraint and cost function, optimization problem, the simulation results, and the conclusion. The introduction is, the water distribution system are a connection of pipes to transport different kinds of fluids. The proper functioning of this system is very important because these are used for the distribution of water in each home, in industries and hospitals and pumping stations. Frequently, the problems on this system are leaks generated by water hammer effect, leakage due to pipe wear, leaks due to the over pressure in the system. This picture represents a leak in a city. The principal problem of the leaks are economic losses, product losses, supply problems, and pressure variability. For this reason, it's important the monitoring and control in hydraulic network system to maintain the pressure and flow at their demand valves. On the other hand, what is the problem statement? The lack of management in this system causes overpressure in some parts of the network, causing leaks and problems in the demands. A simple solution could be to reduce the pressure in the system with a control valve. However, this will affect the demand. For this reason, an optimal solution is proposed to find a trade-off between maintaining the water supply demand and reducing loss due to leaks. A control valve can be represented by this picture. It has a pressure at the inlet, at the outlet, the flow through the valve, and the parameter to adjust the pressure. In this case, the parameter R. The dynamical model of this valve is given by this equation, where H represents the pressure, the Q are the flows, the parameter R, and E represents the output speed of the water through the valve. The equation of the valve is used in the dynamical model of the flow through of the water distribution system. In this case, these equations, where H represents the pressure, Q are the flows, mu represents the friction factor, the QL represents the leak. In this case, this equation represents this diagram with pressure and flow sensors at the inlet and outlet of the system. For the principal objective is to control a critical node, this node, by means of the pressure reducing valve when the system is in leaking conditions, considering the demand. These parameters are given by these equations. For example, the gravity, the area, the length of the pipelines, and the friction factor. It's important to mention that the previous diagram represents the real system. In this case, this is the real system built in the hydroinformatics laboratory from Tecnológico Tuxtla Gutiérrez, Mexico. It's instrumented with pressure sensors, flow sensors, and valves to simulate leaks. To reduce a leak, the following control technique is proposed. Now, what is the control strategy? An MPC controller is proposed to find the optimal valve input to the system, where the input, in this case, this U, and output enter a prediction process to obtain the future output. Now, the optimization is a cost function that penalizes the error of the future output with respect to this reference. This strategy is given by these phases: linearization of the water distribution system, obtaining prediction equations, definition of constraints and cost function definite, definition of the optimization problem. For this strategy, the previous nonlinear system is linearized at each sample time to find the operating points, and the linear system is given by this equation and these matrices. Okay. This vector represents the states, and this vector represents the inputs, where A1 and A3 are given by these equations. In this case, A1, these equations, and the delta parameter represent the difference between nonlinear system, in this case, nonlinear system, and the linear system. Now, the linear system is described at each sample time, okay, are given by this equation. Now, to consider the increment of the input, in this case, these equations, the following augmented system is used, are given by this equation. Okay. This system enters a prediction process. Okay, this vector represents the vector of the states and the input. Okay. Now, the state prediction is given by this equation, where P represents these matrices. For the output prediction is given by this equation. In this case, where the P represents this equation, and this vector represents the offset of the system. The input prediction is given by this equation. Input prediction matrices are this equation, and for the states is this equation. Therefore, the prediction equations are given by the 16, 17, and 18 equations. After the prediction equation, the optimization process is considered. In this case, the cost function. The cost function to be optimized penalizes the future output error with respect to the desired output value R, and control input and load the prediction and control horizon. The cost function is given by this equation, considering these weights. The constraints are given by this equation. The constraints for the states, for the outputs, in the inputs, and the increment. Okay. In this case, the constraints take into account the physical sense of the system. For example, the minimum and maximum value of the states, in this case, the flow. For the outputs, the control pressure. In this case, the control pressure. And for the inputs, in this case, this equation, the minimum and maximum value of the opening valve. Okay. The optimization problem is given by this equation, subject to these constraints, where the H and F are given by these equations. Okay. And where M and N are the matrices for the constraints. Therefore, the control law is given by this equation, where the increment in U is the first element of this increment. The simulation results. pressures and initial conditions. The pressure in the input of the system, output of the system, and the initial conditions for the states. In this case, this value is for the output. The sample time, prediction and control horizon, the weights, the Gaussian noise in measurement, in this case, in the control node, constraints for the input, for the states, and for the output. Okay, for the constraints, for example, the minimum value in the input, in this case, in the input, represent the minimum opening of the valve, and the maximum value represent the 100% opening of the valve. Now, the constraints in the states represent the range of the system flows, and the minimum and maximum values in the output represent the pressure range at the control node, in this case, for the output. The parameters are pipeline length, relative roughness, the density, the kinematic viscosity, the coefficient lambda, setting parameter, gravity acceleration, valve coefficient, and pipeline diameter. These parameters are used to simulate the previous equations or the previous system. For case 1, in this case, leak-free, a comparison between a P.I.D. control and the MPC control is present. In the up graph, in this case, the blue line represents the demand pressure profile. The red line represents the pressure controlled by the P.I.D. And the yellow line represents the pressure controlled by the MPC. Therefore, we can see the efficiency of the MPC with respect to the P.I.D. The low graph shows the control inputs of both controllers. Okay, for case 2, in this case, a leak is considered. In the up graph, the black line represents the leak-free demand pressure profile. In this case, a leak is present at this time. We can see this effect. For this reason, the blue line set point reduce the pressure in a period of minimum demand to reduce water losses. In this case here. We can see that the control pressure, the red line, follows the blue line when a leak occurs. Okay. It's important to mention that the pressure is reduced in the periods of minimum demand for not to affect the supply. With this strategy, we have a 5% reduction in leakage. Now the flows. Finally, this graph shows the reduced demand flow due to leak, in this case, this reduction. The blue line is the free flow. The blue line is the free flow of leakage, and the red line, the reduced flow. Okay, the conclusions are: a model predictive control for the management and control of water distribution systems was present in this paper. The main contribution was to consider a control strategy to find a trade-off between maintaining the water supply demand and reducing losses due to leaks. This problem was formulated as an optimization problem with the states, input, and output constraints. Simulation results illustrate the proposed controller's performance and robustness to track the desired pressure demand and reduce water losses due to a leak with an average of 5%. Thank you very much.